Okay, so let us begin once again with the recap. Okay, so in the last few or maybe just the last lecture, we have been looking at construction of finite fields. Okay, so we looked at construction of fields with p power m elements, right. So we looked at, we denoted it either as f p power m or g f p power m. Okay, so these are finite. Okay, so they have a finite number of elements. So this p and m we can give them some names. So the p is called characteristic. Okay, m is usually not called anything. If you want, you can call it exponent. Okay, or you can just say m. Okay, so p is called the characteristic of the field. The reason why it is called characteristic is basically p equals 0. Okay, right, in that field p is the same as 0. So that is why it is called the characteristics. That is the reason. Okay, so let us do a recap by looking at 3 very prominent examples which we will use quite often in this course at least. Okay, so the first example I want to run through once again is F4. Okay, so F4. So moment I say a field with 4 elements, okay, what are the immediate things that you already know? Okay, so p is 2 and m is 2. So characteristic has to be 2, okay, and m will be 2. All those things you immediately know. Okay, so moment I say 4, you know all that. Okay, and then this F4 worked out to have this form, right, 0 1 alpha 1 plus alpha, and then okay, what else do I need to describe this field completely? I need the primitive polynomial. Okay, so I will have to say alpha squared plus alpha plus 1 equals 0, right. So this is the thing, and with this it will turn out that you can also show that this field can also be written as 0 1 alpha squared, alpha power 3 is 1, and then or say alpha square is alpha plus 1. Okay, so all these things are equivalent ways of describing this field. Okay, so one can show that this is a proper field. You can check all the axioms. What are the main axioms in a very high level? You have addition with inverse and then multiplication with inverse, except for 0 everything has an inverse, multiplication is closed. Okay, so those are the things that you can check quite easily here. Okay, the inverse is also very easy to find, all that is fine. Okay, so if you want some kind of a representation or a table for this field, it's common to write the table in this form. Okay, so you can write a table. It has just 4 elements. Okay, 0 1 alpha and 1 plus alpha. Okay, so this is the polynomial notation, and then you have the power notation. What is the power notation? 0 1 alpha squared. Okay, so these are 2 ways of representing the 4 elements of this finite field with 4 entries. Okay, so both these notations are useful. What are they useful for? The polynomial notation is useful for what? For doing addition. Okay, and the power notation is useful for doing multiplication. Okay, if you have to do both multiplication and addition, what would you do? Go back and forth with this. Okay, so whenever you have to add, say for instance alpha plus alpha squared, okay, what can you do very easily? Go to the polynomial notation and find that it is equal to 1. Okay, so in F4 really it is not very complex. Addition and multiplication are very easy, but in larger fields such things will be very useful. Okay, so the polynomial notation sometimes is also written as a vector notation. Okay, so what would a vector notation mean? Okay, so there is also this vector notation for polynomials. I do not seem to have room there, so I am going to erase this and then write the vector notation next to it. Okay, so I will write the conditions here. I will write the vector notation here. Okay, so the vector notation is also popular. So basically you write the coefficients as vectors. Okay, remember what is F4? F4 has polynomials with coefficients from F2 of degree less than or equal to 1. Okay, so it will have two coefficients, the constant term and the linear term. Okay, so you write both the coefficients as vector. Okay, so this would be 0 0, this would be 0 1, this would be 1 0, this would be 1 1. Okay, so what is the advantage of the vector notation over the polynomial notation? There is no advantage. Okay, that is the truth. I just asked you a trick question. Okay, but if you want to write a computer program, you might want to think of a vector as something that you can represent, but still it does not really matter, it is all the same. Okay, there is really no advantage for the vector notation as compared to the polynomial notation. It is used, so you should know that it is used. Okay. Yes.
Notation is not complete unless we write the conditions.
Yeah, I mean these conditions are crucial. Of course, these conditions are very crucial. So usually on top you have to say what the primitive polynomial is. You have to say this. Once you say this, it's okay. Okay. So when I define F4, yeah, but still, I mean you have to say that condition. Yeah, it's right. If you just look at it algebraically by looking at this, it's not consistent unless you say alpha square plus alpha plus 1 is 0. Okay, so that's F4. Okay, I'm going to make a table like this for F8. Okay, and I'll also urge you to make a similar table for F16. Okay, it's important that you do it for various reasons. I mean, definitely it will be useful for you for problem solving and all that. Okay, so let's do that for F8. For F8, okay, you have 8 elements, of course, 0 1. So once again, once I say 8, the two things you can figure out are P and M. Okay, so 8 is 2 power 3, so clearly characteristic has to be 2, and the field is made up of polynomials in some alpha with coefficients from F2 and degree less than or equal to 2. So those are the 8 elements that you have. So if you want, you can write it down, alpha 1 plus alpha, then you will have the alpha square terms, right? Alpha square plus 1, alpha square plus alpha, alpha square plus alpha plus 1. Okay, and then the primitive polynomial is important, right? You have these 8 polynomials, then what is the primitive polynomial? Yeah, you can take any one of two possibilities, we will take this one. Okay. Alright, so that is F8. Okay. So to make the table, the polynomial versus power table, it is good to go from the power notation to the polynomial notation. Okay, so it's something that I use. You might also have other ideas to do this, but this is one idea which works quite well. Okay, 0 and 1 are the easiest. They remain the same in both notations. So no confusion. 0 is 0 and 1 is 1. Okay. By the way, there is one thing you will find, for instance, if you look at MATLAB, in the power notation, you can't write 0 as alpha power anything, right? It goes from alpha power 0 onwards. 0 is nothing. Okay. So what they usually do is, they say in the power notation minus infinity, alpha power minus infinity is 0. So in MATLAB, the symbol minus capital I and F is used for 0 in the power notation. Okay, so if you are doing Galois field arithmetic in MATLAB, you might see that usage. Okay. In the polynomial notation, there is no confusion. Sometimes the power notation they use minus infinity. On the other hand, the latest MATLAB only uses the polynomial type of notation. Okay, you cannot have anyway. So minus infinity is sometimes used for 0. I just wanted to point that out. Okay. So alpha power 0 is 1. Okay, and then you have alpha power 1, which is just itself. Okay. Then alpha squared is also alpha squared. Up to here there is no problem in the polynomial notation. Then when you go to alpha power 3, clearly it is not in the list of elements I have in F8. Okay, but I know I can simplify it using the primitive polynomial, right? So that is the idea. So alpha power 3 would become alpha plus 1. Okay, so you simply use this equation here to get alpha power 3 to be alpha plus 1. Then alpha power 4 is quite easy. Okay, what do? You simply multiply the previous thing by alpha. Okay, so that is the idea you can use to build this table very easily. See, alpha power 4 is alpha power 3 times alpha. So, when you multiply this by alpha, you get alpha squared plus alpha, and that is very much in the F8 that I have written down here. Okay, and then you have alpha power 5, for which once again you have to multiply the previous thing by alpha, but then what would you get? Alpha power 3 plus alpha squared, and then once again the alpha power 3 has to be substituted again. So, you would pretty much get alpha squared plus alpha plus 1. Then the last thing, alpha power 6, you can write down by elimination, which is alpha squared plus 1, or you can do the computation again, you will see you will get alpha squared plus 1. Okay. So, this table is crucial if you want to do any computations with finite fields. Okay. So, for instance, if I give you a matrix with finite field entries and you have to do Gaussian elimination on it, then this table becomes crucial. Okay. So, when you do finite field, when you do row operations, you are doing you have to know what the finite field arithmetic is. Okay. For that, this table is fairly useful. Okay. So, we will come back and see that a little bit later. Okay. So, this part is clear, right. So, this is how you construct F4 and F8. If somebody asks you what is F4, you should not say I do not know, no, you should say I know F4. F4 is simply 0 1 alpha alpha squared, with alpha squared being equal to 1 plus alpha and alpha power 3 being 1. Okay. So, that is the very simple way of defining it. Okay. So, for F16 also you can do a very similar thing. Okay. I am not going to do it, I will simply write it down just to show you how you can easily write down alpha alpha squared all the way till alpha power 14. Okay. I will write it in the power notation because it is very easy to write in the power notation. Okay. And then, but the primitive polynomial you have to say what it is. Okay. So, for instance, one thing you can take is alpha power 4 plus alpha plus 1. Okay. If you use this, you will get alpha power 15 to be equal to 1. Okay. Remember, you can write this alpha power 15 equal to 1 quite easily by the fact that this is a primitive polynomial. Okay. Right. So, because you remember by the definition of that polynomial, the smallest n for which it divides x power n minus 1 is when n equals 15. So, it will divide. Okay. So, you might ask, will it always divide any polynomial of that form? It turns out it will. I mean, all those things we will not see in this course at least. So, it is a very consistent definition, do not be worried about why that definition makes sense. Okay. So, it makes a lot of sense, it will divide 15. Okay. So, that is the result here. Okay. So, for this also now you can make a table, right. You can make a table. For instance, if I ask you to do some summing up, for instance, let us say alpha power 5 plus alpha power 6. If I ask you this, right, what would be the answer? Okay, in this case it is maybe a little bit easy because one of those equations will readily give you the answer if you multiply both sides by alpha power 5. Okay, so you get okay. Anyway, it does not matter. So, the ready made way of doing it is to have that table. Once you have that table, you go look up what alpha power 5 is, and then you look up what alpha power 6 is, then add it up, you will get the answer in the polynomial notation, and then you can go back to the power notation. Okay. So, let me do that real quick for this case. Okay. So, in the power notation you are getting 0 1 alpha squared, alpha power 3, alpha power 4, alpha power 5 would be what? Alpha power 4 is 1 plus alpha. What would be alpha power 5? Alpha plus alpha squared. What would be alpha power 6? Alpha squared plus alpha power 3. So, now you can do this addition. So, let me do a few more just to get to the point where this will come alpha power 3 plus alpha plus 1, then alpha power 8 is alpha squared plus 1, then alpha power 9 is alpha power 3 plus alpha. Okay. So, with some foresight I know the answer will come within this. Okay. So, let us say alpha power 5 plus alpha power 6, how do I do this computation? Okay. So, this is the table. I am assuming this table is given to you or you have generated it using the equations I have given you. So, how do you do to do this summation? You substitute what you have for alpha power 5, that would be alpha plus alpha squared, and then you use what you have for alpha power 6, what is that? Alpha squared plus alpha power 3. So, these two when added, what do you get? Alpha plus alpha power 3. Is that okay? Okay. So, now you go back to this table and look it up, you see that this is the same as alpha power 9. Okay. So, using this I can now say that these two things will add up to give me alpha power 9. Okay. Another thing you can do is you can take this equation alpha power 4 plus alpha plus 1 equal to 0 and multiply by alpha power 5. Okay. So, you directly get the answer alpha power 9. That is what I said, this addition is very easy to do in this equation, but there is a more algorithmic way of doing it. This is maybe a creative way of doing the answer, but the algorithmic way of doing it is to just look up this table and do it. Okay. So, this, yes.
You get keep.
Yeah, it's the same as what I did with the multiplication. Okay. So, for instance, if you have to do a little bit something a little bit more complicated, let us say alpha squared plus alpha power 9. Okay. Okay. So, it is not very obvious what it is. Okay. So, you have to look it up. So, you have to find out alpha power 9, okay, then you will get alpha squared plus alpha power 3 plus alpha, okay, and you have to look it up in the table. So, we have not gone all the way up to there. Okay. So, if you do that, you will get the answer. Okay. What do you think the answer is? Let me see who is going to tell me what this works out. 11. Alpha. 11. Okay. So, enough people are saying 11. So, you would get 11. Okay. So, I mean these are the kind of computations that you have to become comfortable with doing. This is how you work with finite fields. Okay. So, the only field that you might be very familiar with is the, I do not know, let me not take a guess here, but rational field I guess is most people are quite comfortable with doing additions and multiplications and real numbers also, if you have a calculator maybe, right. So, things like that you can do very easily, but when you do complex arithmetic, you are implicitly doing something like this. Okay. So, remember every complex number you write it as a plus bi, and then whenever you multiply, what rule do you use for I squared? I squared is minus 1. Okay. So, that is very similar to this rule, right. So, this is actually something very similar happening here also. Okay. So, you write a rule for this alpha and then you do the multiplication with that. Okay. So, that is the idea, alright. So, it is a bit of a pain to go from power notation to vector notation or polynomial notation and back, but there is no other way to do the computation. Okay. In a way it is easy, but it is also little bit time consuming. Okay. If you are not comfortable with this, if I give you a 5 by 10 matrix with entries from F16 and ask you to do Gaussian elimination to find rank, it will take the better part of 1 hour exam, okay, and then you can't answer any other question following. So, it is a good idea to practice these things. So, be comfortable with what the arithmetic is. Okay, it is fairly crucial. Any questions on how the arithmetic is working out? You are okay? Alright. So, the next thing I am going to do in this lecture is to give you a brief idea for why is for some abstract reasons why all finite fields will be this way. Okay. I won't do it completely, I won't give all the proofs, but just a brief idea from a high level for why there will be no other finite fields. Okay. So, what are these? There are a couple of facts which are quite interesting, which you should know, but maybe in an advanced course you will see a proof. The first fact is if f is a finite field, what do I mean by a finite field? A field that has a finite number of elements. Okay. So, this implies size of f, that is the number of fields in f will be, number of elements in f will be equal to p power m for some p which is prime and m which is a positive integer. Okay. So, this is a reasonably a powerful statement, and we will see a fairly complete proof of this. It is not too difficult to prove this. Okay. So, off the top of your head you might think this is a very impressive result, right? Do you think or not? Okay. So just because I say f is a finite number of elements and it's a field, it has to have the size p power m. Okay. So I'll give you a simple argument. It's a bit of an abstract argument. If you don't follow every step, it's not too crucial, but just to give you a feel for how these proofs work. Okay. So suppose I tell you f is a finite field. What are the possible elements that f can have? Okay. So the first element that you know for sure f will have is the additive identity 0. The next element which you can be sure it will have is the multiplicative identity 1. Okay. Beyond that you really don't know, I mean it's an abstract field. I mean it has a bunch of elements and it follows all those rules. These are the only two things you know. First things you might suspect is maybe 1 is equal to 0. Okay. If 1 is equal to 0, then there will be nothing else in the field. Okay. So it becomes a very trivial, ridiculous little field. So you don't worry about it too much. Okay. And then you ask the question, what else can I create from these two elements? What field operations I can do with these two elements to maybe generate more elements in this field? Okay. What can I do? Okay. Yeah. So the only thing you can do to generate non-trivial elements of this field is to take one and add it to itself. Okay. Because anything else you do, you will get only the fields that are elements that are in this. Okay. So you can take one and add it to itself. Okay. So you might want to do say 1 plus 1. Okay. I have no idea what this element is, but this 1 plus 1 has to be in the field. Okay. Then you can do it once again, right? So you can do 1 plus 1 plus 1. Okay. So or I can use a shorthand. I can represent 1 plus 1 as 2 times 1. It's just a shorthand notation for 1 plus 1. I don't want to keep on writing 1 plus 1 plus 1. So instead of 3, when I added 3 times, I might say 3 times 1. So that's all these guys must be there, and eventually what should happen? Can it go on and on and on forever? No, the field is finite, right? I know the field is finite. It has to end somewhere. Okay. So there has to be an n times 1 which will repeat, okay, which will give you another thing. How can I know that it will be in the same set? Okay, those things, so you believe me when I tell you, it will be there. Okay. It will be one of these things only. Okay. So you have to, there has to be n times 1 which has to repeat, and it has to repeat in 0. Okay. Because if it does not repeat in 0, you can do some small, with respecting the field axioms, you can show that there is some violation. Okay. So it has to result in 0. So there has to be a minimal n times 1 which will become 0. Okay. So this is minimal n such that n times 1 is 0 in this field. Okay. So now without too much effort you can show that this n has to be prime. Okay. So maybe with too much effort, I don't know, you can show that n has to be prime, because if n is not prime, if n is a times ab, then you can take a times 1 and show that when it multiplies with b times 1 you will get 0. Okay. So which means either a times 1 has to be 0 or b times 1 has to be 0. Okay. So these are all things that you can prove with abstract field axioms. You don't need any actual field elements to show these things. Okay. So using some arguments like that, you can show n has to be prime. Okay. So let us say we will take n is prime. So if a number is prime, it's violates some law to call it n. Okay. You have to call it p. Okay. So you make it p. Okay. So you know in this field you will have elements of the form. Okay. So n is prime, so you call it p. Okay. Okay. So this p is called the characteristic of the field. So that's why you call it characteristic. So p is equal to 0, and that's the minimal p that will be 0. P times 1 will be 0. Okay. It's also very common in fields to write 2 times 1 as 2 itself. Okay. So you don't have to say it's 2 times 1, you can say it's 2. Okay. So now just because I said f is finite, I already know f has elements of the form 0 1, 2 times 1, 3 times 1, all the way to p minus 1 times 1, and then p times 1 it won't have, p times 1 it comes back to 0. Okay. So maybe some other elements. Okay. Now the next thing you show is this guy here is actually what is known as isomorphic or very similar to fp. Okay. So you can show this is fp in disguise. No, you can do a very simple proof of that. It's not too hard. Okay. Just laborious writing you have to do based on the axioms to show that this is fp. Okay. You can identify 2 times 1 with 2 itself, 3 times 1 with 3 itself, and you see every addition and multiplication will be consistent whether you do it in this abstract field that I don't know about, or you can do that same thing in fp and you will get the exact same result. So these two will be isomorphic. It is not too difficult to prove, right? P is equal to 0 and P is equal to 0 in my FP also, right? And we do the any addition or multiplication, remember this is all 1 plus 1 plus 1. So if even if I do multiplication or addition, it is same as multiplying integers and adding integers mod P, okay. So it is not too difficult to show that, okay. So you see this is FP, alright. The next step is a little bit more abstract. What you can show is, once you know that FP is contained in F, okay, so in some isomorphic form, and F is a finite field, Fp is contained in this and P is 0, right, all that is true. So what will happen is F will become a finite vector space over Fp, you can show that also, okay. It is also not too difficult, you can prove all those axioms for abstract vector space, okay. So you can show not only is Fp contained in this F, F is a vector space over Fp, okay. Now that is enough to show that size of F has to be equal to P power m for some positive integer m, yes or no? No. See, F is a finite set, so it is a finite vector space, finite dimensional vector space over Fp, which means what, there will be some dimension for it, okay. So you will have, let us say m is the dimension, okay. If you have dimension m for a vector space over Fp, it has to have only P power m elements. How will I know that? There will be m basis vectors and you take just m possible coefficients to multiply and add them to make linear combinations, you get all vectors in F. So clearly it has to be P power m, okay. So that was a very quick half a page argument, but usually if you read a book it takes some time to write it down, you know, I mean you have to carefully write it down. So all those things when you write down you can show, just because F is a finite field, the number of elements in F has to be equal to P power m, where P is some prime and m is some positive integer, okay. So it is not too difficult from here to show a polynomial notation, and then you have to show primitive polynomial, all those things are not very hard, okay. What is a little bit involved is to show the existence of the primitive element, okay, of that one element which will generate all the elements of this Fp by powers, okay. The power notation is a little bit more tricky to prove, but there are proofs, there are very much eminently elementary proofs for that fact also, okay. If you are interested I can point you to some good references for that, okay. So that is enough of abstract stuff, okay. So I am sure you are wondering, F is a finite field, but what do you mean it is abstract, it does not exist? I mean, of course it exists, okay, do not worry about it. So what is more important for you is this table, okay. So this kind of tables you should be very comfortable with, okay. So once I tell you F8, you should know that I have to look for a primitive polynomial of degree 3 with coefficients from F2, okay, and then I should be able to write down both the power notation and the polynomial notation. Once I do that, I can do any computation I want in F8, okay. That is the basic idea, okay. In your tutorials maybe there will be some problems to help you get acquainted with these computations, okay, all right. Okay, so that takes me to some, okay, so let us see some mildly interesting coding stuff with these fields before we move on to really good codes, okay. So what did I promise you when we embarked on this finite field adventure? D equal to 5, right. So we will not see D equal to 5, we will just see D equals 3 for now, but still you will see that finite fields give you something more, okay, something slightly better than what you had with F2, okay. So with F2, okay, so let us see some examples of code construction. For D equals 3 only, okay, I am not promising anything beyond that, let us see for D equals 3 first, okay. So let us say we start with just F2 first, okay, just binary codes. I want to construct a parity check matrix with 2 rows, okay. So this is my parity check matrix, I want to have D equals 3, I want to have 2 rows, okay. What is the maximum n that is possible? 3, right, I can't do better than 3, okay. So I can do 1 0 0 1 and I can do 1 1 and I have ended here, okay. So I can't do anything more, am I right? Because anything else I do, it is going to become linearly dependent, there is no problem. Okay, so n equals 3 is the max. Okay. So now let us try to think about the same question, but with F4. Remember what is F4? 0 1 alpha alpha squared, alpha path 3 is 1 and alpha squared is 1 plus alpha. Okay, so this is F4. Okay. Let us try to ask the same question, but now I have to be a little bit careful here because I did not really define codes over F4. Okay, we have defined codes over F2, but I did not really spend a lot of time defining codes over F4, but let us just briefly try to construct a parity check matrix, okay, which will satisfy the constraints for D equals 3. So remember what is the constraint for D equals 3 for the parity check matrix? No all 0 column, no identical columns. Is that enough for F4? Okay. So no two columns must be linearly dependent. Okay, so you should rephrase that a little bit. In F2 it was the same as identical, in F4 it is not the same. Why? You can have two non-identical vectors which are linearly dependent in F4. Why is that? Okay, so you could take for instance 0 1 and 0 alpha. Okay, these two are not identical, but they are linearly dependent. Why? Okay, okay, so you somehow disagree with that because is it okay? Is everybody okay with that? These two are linearly dependent, right? So it's like they are on this y-axis. Both of them are on the y-axis. If you think of this top thing as the x-axis, bottom as the y-axis, both of them are on the y-axis. Okay, so you multiply this guy with alpha, you get 0 alpha. In fact, even this guy is linearly dependent. Okay, if you want a slightly more complicated example, you can have 1 alpha and then what? Alpha alpha squared and alpha squared 1. These three guys are also linearly dependent but not identical. Okay, so linearly dependent okay. So those two conditions are enough, right? You cannot have the all 0 column and you cannot have two columns being scaled versions of each other. Okay, so you cannot have linearly dependent columns. Okay, so now let us try to construct a parity check matrix like that. Once again with R equals 2, okay, you have to tell me what the max n is. It seems simple enough. How many columns can you have? Is it just 3? Can you do more than 3? No, you can't do more than 3. You can't stare at the board and answer this question, you would write something down. No, just try, give me something with n equals 3 first. Okay, so let us do 1 0 you can put, right, 0 1 you can put. Now what does this rule out? First of all, how many possible length 2 vectors are there with F4? Why you say 4 C2? It's 4 for the first and 4 for the second, that is 4 squared, that is 16 different length 2 vectors are there over F4. Okay, so it's a very simple computation, but think about it for a while. Is that right? You are convinced? Okay, 16 different. Okay, there will be one which will be just 0 0 and that is ruled out. I can't do it. So I have 15 different choices for each column. Okay, but if I select one column, how many columns, how many vectors get ruled out? 2 others get ruled out, right? What are the 2 others get ruled out? Well, that row, that column itself gets ruled out, that is 1, and then 2 others. Okay, what are the others? Alpha times that and alpha squared times that. Do you agree? Okay, those 3 get ruled out. Okay, so the moment I put 1 0, I cannot put alpha 0 or alpha squared 0. The moment I put 0 1, I cannot put 0 alpha squared or 0 alpha. Then what else can I put? Just take anything else. Let us say 1 1. If I take 1 1, what can I not put? Alpha alpha, alpha square, alpha square. Is there anything left? Yeah, definitely 1 alpha is left, right. What about 1 alpha squared? 1 alpha and 1 alpha square are not linearly dependent. 1 alpha square is also there. Okay. Now I cannot really do more. Okay. So maybe you can't prove it, but min max n in this case will turn out to be 5. Okay. This has ruled out everything. All the other vectors are linearly dependent with one of these things. You can pick, there are various other choices. I am not saying this is the only choice for the h, but this is one of them which satisfies the condition for d equals 3. Yes or no? Yes. Okay. What is the rank of this matrix? 2. Yes, because you have an I sitting there, right. So it has to be 2. Okay. So n is 5, n minus k is 2. So you have 5 comma 3 comma what is d? It is equal to 3. Can you find a code word with 3 non-zero entries? Yeah. So question is, do you have 3 columns which are linearly dependent? Yeah, very much. It's definitely there, right. The first 3 columns are linearly dependent. Okay, and several other, I think any 3 if you take, it will be linearly dependent. Okay. 533 code, no surprises. What type of a code is this? It meets one of those bounds that we had. Okay, it is an MDS code. Okay, so d equals n minus k plus 1. So this is an MDS code. Okay. So it will meet the singleton bound. Okay. So something you cannot do with binary. Okay, for r equals 2, right. For r equals 2 in binary there is no, unless you have some trivial like n equals 3 or something, it is there, but if you have larger n you can't have, there is no non-trivial bound code that meets the singleton bound. So once you go to F4 you have a code that meets the singleton bound. Okay, so it gives you something more, you can see it very easily. Yes or no? Okay, but I am actually cheating a little bit here, but maybe right now you can't see it immediately, later on I will point out what is the cheat, okay, what the cheat is. At that time you will know, oh really, that will be your response when you see that, but anyway it does not matter, at least from nkd you get a larger range by going to from F2 to F4 definitely. Okay, and you can also get to d equals 5 and all very easily in a very systematic way, that is the real selling point, right. This is not the major selling point. D equals 3 you anyway know how to do, in binary it is not much better. Okay, take some time to digest this is an important thing. I am going to ask several more questions after this, but let us see. Is it okay, everybody convinced? Okay. Alright, so now let us look at this parity check matrix a little bit more closely and try and do something with it. Okay, so just to learn what is this. What is alpha exactly? What is 1 exactly? That is the question you would ask. Okay, so it does not matter what alpha is, right. So it just obeys certain rules for multiplication and addition. Yeah, so that is a question that most people have when they learn abstract algebra for the first time. What is alpha? Okay. So you should find out first what does what mean. Otherwise you can't ask that question. Okay, that's a difficult question to answer. What does 1 mean? Okay, so you're usually used to counting, and so you say 1 is 1. But what is 1? Right? It's not, the only way you define 1 is when it adds to itself, it gives you 2. But what is 2? So it's not. So at the end of the day, even the familiar numbers that you know are abstract. Okay, just that yes, you're familiar, learnt it from whatever preschool or second standard or something. So you don't question it too much. So these are also like that. You shouldn't ask what alpha is. It's not a question that is relevant. Okay, right. So in the Greek alphabet, alpha is the beginning, the first letter. That's the way to think about it. Okay, so let's look at this. So I talked about a parity check matrix, and like I said, I haven't strictly defined codes over a finite field, an arbitrary finite field. I'm going to do that real quick, but with this example first and then we will formalize it. Okay, so it is a bit easier to see it that way. Okay. So suppose I want to think of a code word defined by this parity check matrix. What am I actually saying? Okay, the code is basically what? Set of all code words in what? In a vector space. What is that vector space now? It is not F2n, it is F4 5. Okay, so what is F4 5? The 5-dimensional vector space with coefficients from F4. Okay, so you have to think of this as things of this form: V1, V2, V3, V4, V5. Each Vi belongs to what? F4. Okay. So how many vectors are there in F4 5? In F4 to the 5, how many vectors will there be? 4 power 5. Okay, and what is that? 1024. Okay, 1024, 2 power 10 counter. So it is a very finite vector space, alright, such that what? H times C transpose is 0. Okay, so this definition carries over for the parity check matrix. I do not have to worry about anything here, right, but except now what are the operations in H times C transpose? Over F4, it is not modulo 4. Okay, so a lot of people after a course in finite fields always say F4 is 0, 1, 2, 3 mod 4. It is not true. Okay, totally not true. That is not a field, it does not work at all. F4 is a completely different thing. 0, 1, some god knows what alpha, and then an alpha squared also. Okay, so and then alpha power 3 is 1 and alpha squared is 1 plus alpha. So those are the abstract rules that you have to follow when you deal with these numbers. Okay, so those rules are basically the field. F4 basically defines those rules, and when I say H times C transpose, previously I could just say modulo 2 and you were happy about that because everything was binary. Now everything is in F4 and the only thing I can say is operations over F4. I can't say modulo anything, it is not modulo anything. Okay, so it is operations over F4. Okay, so now F4 is a proper field, F4 to the 5 is a proper vector space. So all the results you had from rank and Gaussian elimination carry over to that also. Okay, in the linear algebra setting everything works. It is a field, it is a vector space, so there is no problem. Okay, so for instance rank of H is 2. Okay, which means if you want to find set of all C, you will have 3 free variables and 2 dependent variables. Okay, so this null space of H, this defines the null space of H. Null space of H will have dimension . Okay, the row space of H has dimension 2, which means the null space of H will have dimension 3. Okay, so that result carries over without any problem. Okay, so you notice rank of H equals dimension of what? Row space of H equals 2. Okay, I mean you can prove this by doing Gaussian elimination. Okay, and here in this case Gaussian elimination is already done. Okay, you already have the 0, 1, 1, 0, so there is no problem, you can immediately write 2. What is the dimension of the column space of H? Is it equal to rank of H? It is equal to rank of H. That result is also true, there is nothing wrong with that. Okay, all the results that you knew from linear algebra carry over without any change in this setting. Okay, even though you do not know what alpha is. Okay, so remember the proofs there you might have learnt it being very conscious of the real field all the time. Okay, but you can do linear algebra without reference to anything about the real numbers. Okay, you won't have used anything about the real numbers except that it is a field and you can do division and addition, etc. Okay, I mean I do not know, depending on how it is taught. I think the way it is taught in math methods you do some abstract stuff also. Okay, so you know how it works. Okay, so column space also has the same dimension. So if you want to look at the null space of H, remember C is the null space of H, right. This will have dimension what? Okay, it will be number of columns minus rank of H. Okay, so it will be 5 minus 2, which is 3. Okay, all these results carry over to arbitrary abstract vector spaces over abstract vector fields, abstract finite fields, there is no problem. Okay, so it just works without any worries. Okay, so that is the advantage of learning abstract. When you are asking me what is alpha, I do not know what is alpha, you should not learn it. No, I mean when you abstract everything out, the same thing applies to anything which satisfies those minimal axioms. What are the minimal axioms that are needed? Okay, so and you have that power with you when you know it in abstract. Okay, when you do not know it in abstract, you are not sure, okay, it works for real numbers, does it work for this, does it work for that, you are always confused. When you learn it purely in abstract, that is the advantage. Okay, so this is true. Okay, so basically what does it mean? Once I say null space of H has dimension 3, when I try to solve HC transpose is 0, I will get 3 free variables and 2 dependent variables, and the way I have written it down here, you can associate the free variables to the message part and then the dependent variables to the parity part, okay, which is what we did in the binary case, right. So now M1, M2, M3 belong to what field? Each Mi, what is Mi? Mi belongs to Mi, just one, we say M1, it belongs to F4. Okay. Everybody is really scared now to say anything. So Pi also belongs to F4. Okay. So now I cannot say bits anymore. So M1 is not a bit. Okay. M1 is actually what? Yeah, you can call it a symbol, okay, or an element of F4. Okay. So it is common in communications parlance to call it a symbol, okay, for instance. Okay, it is a couple of bits. Okay. Is it 2 bits? Can I say Mi is 2 bits? Yeah, I mean it is 2 bits. You can represent it with 2 bits. Okay. So, but it is a little bit more because you know it is an element of F4, so you can multiply things. Okay. So it is a bit different. Okay. So what we are going to do next is, it's only like 3 minutes left, so I am going to ask you to write down some code words of this code. Okay. So it is good practice, it is not too difficult, but I think it will tell you something about the arithmetic involved and how to quickly come up with it, and you will actually believe that there are code words, even though it looks like null space of H, maybe you should write down some code words. So let us write down some code words. So once again let me produce the H. Okay. So few code words. So it is easy to write down the message bits first and then ask you for the code. The first code word is the easiest code word, is let us say 100. If my message is 100 or maybe 000, if my message is 000, let us start with a much more basic question. If my message is 000, what is the code word? 00, right. So I mean you just plug it in here and multiply it out, you can do it in your head. So we will do it for a slightly more complicated example. So if it is 100, what happens? One one. Okay. You agree or not? Okay. So remember, when I put 100, what am I expecting? I want to find P1, P2 such that H times P1, P2, 100 equals what? 00. Okay. Let me do this multiplication. When I do this multiplication, what happens? P1 times 10 plus P2 times 01 plus 1 times 11 plus 00 and all that. Okay, this equals 00. Okay, so this is the same thing as what we saw before. So from here you will see in the next step you can do this. P1 P2 equals what? 1 1. Okay, is it -1 -1 or 1 1? Why is it same? We are in F4, no, we are not in F2. Yeah, it is characteristic is still 2. So that is the technical way of answering the question. Okay, you can say F4 has characteristic 2, which means -1 is 1. Okay, that is the way to think about it. 2 is equal to 0 in F4. Okay, that is the way it works. So P1 P2 is 1 1. Okay, so you can do this computation in your head with matrices. Okay, so for binary you might have done it very quick, but in F4 it will take a little bit more practice to get used to it. But remember, this is just I. Okay, right? I am multiplying I with P1 P2. So, essentially what I will have is P1 P2 to be equal to this part 1 1 1 alpha squared times what m1 m2 m3. So, the moment I give you m1 m2 m3, all you have to do is scale these 3 rows, these columns with m1 m2 m3 and then add it up. That is the only operation you have to do, that will be equal to P1 P2 and you can simply put that down here, okay. Right. For bits it might be very easy, simply you have to simply multiply and XOR, that is all, nothing more. For F4 it will be a little bit more complicated, but you can do it, okay. So, time's up now, so we will pick up from here in the next lecture.